Hi everybody, here is the lecture on uniform circular motion. Gravitation will be a separate video. Now when you look at the tracks on a compact disc, you find that you have circular motion right there. You have a lot of circular tracks. And I'm just focusing on 2 points, 2 different points. You can see that the radius of the circular path for one will be smaller than for the other, right? So when the CD spins, the angular velocity will be the same for both, because they both complete the same angle in the same time. Because when this makes one complete circle, that's 360 degrees. This also makes the same complete circle in the same time. So their angular speeds are the same, but their linear speeds are not the same. The particle that is at a bigger radius is going to have a bigger linear speed. So angular velocity is represented by the letter omega and is defined as the angle divided by the time taken. The unit of angular velocity is radians per second. So angular velocity is angle divided by time. And so angle is not measured in degrees, it has to be measured in radians. Therefore angular velocity is measured in radians per second. Now omega is theta by t. Again, the angular velocity, theta is the angle, and the unit is radians per second. But omega is also delta S by R into T, because angle is actually length of the arc divided by radius. So you see the formula here? Angle is length of the arc divided by radius. So I'm substituting for theta as delta S, which is the length of the arc, divided by radius. So when I do that, I get linear velocity over radius, because delta S by T is nothing but linear velocity. So that's an important relation that gives the connection between angular speed and linear speed. Now to find the relation between angular velocity and linear velocity, we will start with the definition of angle. Angle theta is defined as length of the arc divided by the radius. That is the definition for angle. Length of the arc divided by the radius. Now on both sides, I'm going to divide by delta t. So I divide the left hand side and divide the right hand side with delta t, which I've done here. And then that means automatically this becomes angular velocity, omega, while this delta S by delta t is linear velocity. So delta S by delta t is the linear velocity, and so we get omega is V by R. So that's the relation between angular velocity and linear velocity. Let us now look at how to convert from degrees to radians, because you might need that. Remember, 30 degrees is pi by 6 radians, and so on. But the formula that I'm going to use, I'll give at the end. So 30 is pi by 6, and 60 is pi by 3, 90 is pi by 2. Need not memorize these numbers. Of course, you know that 360 degrees is 2 pi, correct? So 180 degrees is pi. But here is the formula. If you get the angle in degrees, multiply it by pi, divide by 180, you will get the angle in radians. Yet another thing for you to understand is that if there are two objects having the same angular velocity, like A and B, they have the same angular velocity but they have different radii, surely the object A has to have a higher linear velocity. And that is clear because linear velocity is r times omega. Okay, so VA is RA omega, VB is RB omega. Since RB is greater than RA, the radius being greater, the velocity has to be greater. So if two objects have the same angular velocity, but they have different radii, then the one that has the bigger radius will have the bigger linear velocity. Now here is just an illustration of that. When the car moves faster, the tires are rotating faster. So that gives you a relation, a kind of idea between the angular velocity omega and the linear velocity. Because if the car is moving faster forward, then omega is also going to be bigger. And that's very clear from this formula. So if you have big tires for the car, the radius is big. So even when the omega is small, you're going to have a bigger linear velocity. Another point worth knowing is that the direction of the linear velocity is always tangential. So if this is rotating in the clockwise direction, at any point linear velocity is going to be along the tangent. So at any point it's along the tangent. Here I have derived the formula for centripetal acceleration. But let me first introduce centripetal acceleration. Whenever you have an object moving in a circular path, there will be a centripetal acceleration. And the direction of the centripetal acceleration is always towards the center of the circle. So even if the velocity is constant in magnitude, it still has an acceleration towards the center of the circle. So remember that the linear velocity is tangential while the centripetal acceleration is along the radius, which means they are always at 90 degrees. And the formula for the centripetal acceleration is v squared by r. You don't need to know how to get that. Just remember that centripetal acceleration is v squared divided by r, which means if an object is going faster, then its centripetal acceleration is higher. Or if it's going in a smaller radius, again its centripetal acceleration is bigger. Here is a summary of what I just said. Centripetal acceleration is v squared by r. And wherever there is acceleration, there must be a force. So the centripetal acceleration gives rise to a force which is called the centripetal force. All you got to do is multiply the acceleration with mass. So centripetal force is mv squared by r, because force is mass times acceleration. Now, this centripetal force is just a general name for the force that acts towards the center of the circle. If we have a string with an object tied to one end and we rotate it in a circle, in this case, the object is able to go in a circular path because of a centripetal force, which is the tension in the string. So in this case, the centripetal force is the tension in the string. Now let's take another example. When the earth goes around the sun in an almost circular path, there must be a centripetal force. And do you know what that centripetal force is in this case? Yes, it is the gravitational force of attraction between the earth and the sun. All right, let me give you a third example. When your car takes a curve, there must be a centripetal force to keep the car on the road or going along the circular path. And this centripetal force would be the friction between the tires and the road. But sometimes friction is not enough, and that's when you have banking of roads where the outer side of the road is slightly higher than the inner side. So that is banking. In any case, what I try to say is that centripetal force is just a general name. It could be the tension in a string. It could be the gravitational force of attraction, or it could be friction between the tires on the road. Here is an example of the friction between the tires on the road. So the car is taking a curve. This is the center of the circular track, and there must be a force, the centripetal force, acting towards the center, while the velocity is along the tangent. Same thing in a centrifuge, which is rotating at a constant angular velocity. Omega is shown here, the angular velocity is here, it's clockwise, that's the linear velocity, and look at the centripetal acceleration, it's towards the center. Just like in this case, it was towards the center. Once again, reiterating that the centripetal force is perpendicular to the velocity, as you can see, and the larger the force, the smaller the radius of curvature. Now let us get an actual formula for the centripetal force when the car takes a curve. Here is the car, and this is the free body diagram showing all the forces acting on the car. It's on a horizontal road, there is no banking, and the forces are the weight of the car acting vertically down, which is mg, the normal force, which means the perpendicular force acting vertically up, and the centripetal force. What is the centripetal force in this case? Isn't it friction? Yes, it is. So we are going to say that the centripetal force, which is given by mass times velocity squared by r, is friction. Well, what is friction? Remember that friction is given by the product of coefficient of friction times the normal reaction, which is mu times n. Mu times n, and here it is static friction, so that's why it's mu s. So the centripetal force in this case is the frictional force. Hope that's clear. We can rearrange this formula. Remember, n is mass times acceleration due to gravity, because the weight mg is equal to n. See, weight n is equal to mg. So that's what I've done. I've substituted in place of n, I've substituted mg. And that means you can cancel the masses out, and you get the formula for velocity square. Of course, velocity would be square root of that quantity, which means that if you know the coefficient of static friction, the radius of the curve, and the acceleration due to gravity, we can calculate the maximum speed at which the car can take the curve. If you drive faster than that speed, the car is not going to be on the road. It's not going to take a circular path. Instead, it will go straight, maybe into the fields or out, because friction is not enough to provide the centripetal force necessary to keep it on the track. I hope that's clear. And that is why, instead of depending only on friction, the roads are banked. So let us take a look at banking of roads. But to make things easy, we will imagine that there is no friction. It's only banking. So here it is. This is a left turn, so to say. And the road is banked. As you can see, the angle of banking is theta. Remember that this object is not sliding down and inclined, it's going across the road. So we go back to setting up our x-axis and y-axis as normal, as usual I mean, so x and y. And that means when you look at the free body diagram, you have the weight acting vertically down, which is along the y-axis, so you don't do anything to it. But the normal force, by definition, the normal force is perpendicular to the road, right? Now that is neither along the x nor the y-axis, so we need to break that up into its x component and its y component. And looking at this right angle triangle, this is going to be n cosine theta. So you have n cosine theta equal to the weight, and n sine theta provides the centripetal force. That's why I've written n sine theta is equal to the centripetal force. Look at that. Isn't that force acting towards the center of this circular track? Because if this is the track, the center is somewhere here. So that's the centripetal force provided by n sine theta. So n sine theta is mv squared by r. N cosine theta is mg. When you divide one by the other, you get tan theta is equal to v squared by rg. This is the formula that we can now use to find how much the road needs to be banked. All we need is to know the velocity, the radius of the curve, and acceleration due to gravity. Do remember that the second part of this lecture, which is gravitation, is in an entirely separate video that was already made, so make sure that you watch that and study from there. Gravitation is also an important topic which is in the same chapter. Thank you.